Okay, so I'm going to start the whiteboard here. New whiteboard, classic. All right, so this should work. Yeah. All right, so it's working. Okay, so we're going to do that problem. Make a machine learning model that can solve this widgets problem or defective parts in a conveyor belt. So there's a couple of things we want to think about. So we have like, let's say you have, this is like your conveyor belt. You guys can see there. Yeah. So that's your conveyor belt. And then you have like parts on it, and you have a camera. And the camera is fixed and always looking at the same spot, like always looking at the same spot. So if we're looking at this from above, the conveyor belt probably looks like this. We have the camera, and the camera is always looking at that spot over here, right? It might have even some reference that they put in just so that they know more specifically what's going on. And then parts are coming in, right? And then maybe this part has a crack. And then, normal, normal. And then a part comes in. That's what was good. This one again has a crack. Do you see what I'm saying? So I have like two types of images here intentionally, right? But it's not perfect, and that's fine, right? Machine learning is smart enough to figure it out. So essentially, I've said, okay, parts look like this, but there are, of course, some parts that can be defective, and that means they have some kind of a crack or something like that. So I've defined that. All right. So now you have to start answering the questions. So what is X? What is Y? Okay, what is a sample? You see what I'm saying? So what are the classes? Okay, some of those questions sometimes have an easy answer and some have hard answers. So X is going to be a matrix. So think of it as an Excel spreadsheet. So that means, let's say, N rows and then M columns. And then this one also needs to have certain values that we need to figure out. Okay? So which one do you want to answer? What's a sample? Or what are the features? What do you think? Hmm? The pixels in the image are the features, right? So that's the easiest one. So that's why I picked it, right? Because it's an easier one because it's an image. So we have an image here. So now we have to figure out what the size of this image is, right? So keep in mind when you're today, even though it seems like we can do anything, there are limits to the sizes of inputs that can go into machine learning models. So for instance, to train CNNs, we really don't want images that are way too big. 4K, 8K, probably not going to work, right? So you're going to be looking at something like 300 by 300. I think ResNets are actually like 224 by 224. Because even though the image seems tiny, think of everything that is happening in that neural network. All the processing, a lot of memory is being consumed. So, we keep the images kind of small. I would say 1,000 by 1,000 is probably too big. Okay. So if you're planning on training a CNN and things like that for this problem, you have to think of the size of those images. Do you guys understand? So for this problem, you have to define it because I'm asking for the values of N and M. So I need these dimensions. That means that you need to commit to something. So what do you think should be the size of the images? Sure, why not? 224 by 224. Let's go with that. Okay. So are we going to say, are these color images or black and white? Black and white. Why black and white so quickly? Why? Is enough for, true, right? Less data, but also maybe the problem is easy because it's really, does it have this line in there or not? Right? That crack. So actually, that is a good justification, right? That black and white might be enough. Why do you need color for that? You'd have might make shadows or something, but you may not need color for that, right? So in that case, I agree with you, right? So that's important because if it was color, remember the color images, it's not just one grid, but 3 times, right? So if you have 224 by 224, then it's 224 by 224 times 3. A lot more data, more RAM, lots of problems. Although color is very useful in some. So, but we're saying we only want black and white. Okay, perfect. All the images, by the way, and hopefully you start to understand this from the vector space model. We're creating a vector space for all these images. So that means that space has 224 dimensions. For every image to be represented correctly in that space, every image has to have the same dimensions. Do you see that? So you can't have some images that are 224 by 224 and others that are 100 by 100. They're not, how are you going to put them in the same vector space? Do you see that? So what you have to do when you have that situation is that you have to somehow make some images smaller and agree on a specific size. Or if they're too small, pad them. But if you have images, let's say that are, so if you're going with 224 by 224 and you have some images that are, let's say 100 by 100, you got to pad them so that they're 224 by 224 because 224 by 224 means, what is that? 224 times 224? Anyone have that number? If we multiply this, what is it? Anyone? 50,000? 176. 50,176. That means we have 50,176 pixels, and each pixel is a feature. Therefore, our space, which is usually denoted by that, is 5176. Just like this is R3, that would be R 50,176. Yeah, please go ahead. Ages, yes. Yes, continuous. That's a good point. From from 0 to 255. So in images, it goes from 0 to 255. That's actually the way it works. So every pixel will have a value. Like I'm just gonna draw. Imagine this is just one part of an image, right? So this might be 0, and I think that's either black or white, one or the other. And then, but this one might be 22. Then you have one that's 100, 110. This one is 90. Notice this one is going to be 5. So you see that this is how you represent them. They go from 0 to 255. But you can also make them from 0 to 1 by scaling, and it's still you see something meaningful. But yeah, that's a good question. So the scale, so that now I can ask you this question. They're all on the same axis, right? Because every one of those 50,000 axes go from 0 to 255. So you don't have a situation where one dominates over the other. Yet you probably still want to normalize. Because machine learning likes 0 to 1 minus 1 to 1. Does that make sense? Any other questions? Good? Yeah. But yeah, that's a good question. So for images go from 0 to 255. And so the R, 0 to 255. The G, 0 to 255. The B, 0 to 255. And yeah, from lighter to darker. All right. So now the key thing is, as I was saying, you want to keep the images of the same size, right? But we've probably answered a very important question right now, right? We've answered the features. We know the number of features, right? So what does that mean? Do we have a dimension for X or for Y? We'll use every pixel as a feature in this example, right? So how can we use that information to define either N or M? So M is in an Excel spreadsheet, the number of columns, right? And each of those columns would be a feature. Therefore, M in this example, because you selected 224 by 224, is 50,000 176. Do you see that? You've defined that now. So that's what's great about it. This is very important because this now is a value you will use to define your neural network. Okay? Questions, guys? All right. So features correlate to M, which correlates to the columns in X over here. What else do we? Oh yeah, go ahead, please.
So it has to be a CSV that's just one. Like we wouldn't. I guess when I imagine it,
I get your. This is a good question. It's a good point. So what you're saying is, I call this spaghettifying. So you usually have these images, right? But neural networks. So a plain vanilla neural network does not take grids. It can only take a spaghettified grid. However, a CNN can take grids. So that's the difference. So what you're saying is, we have this image like this, right? These are the rows. And just for I'm going to say it's 5 by 5, just, to keep it simple. But a plain vanilla neural network needs to take only a vector, like one-dimensional, not two-dimensional. So what we do is we spaghettify, which essentially means I grab this one and I do that. Then I grab this one and I concatenate it. You see that? Then I grab this one and I concatenate it. And then finally I grab this one and I concatenate it. So before this was 5 by 5. Now this is from 0 to what? To 25, right? 5 times 5. I stretch. You can also think of it as like yarn. So you pull on the strings and the thing becomes just the string itself, a one-dimensional vector. So if we were building a simple neural network, the input layer would be 25 features that go into the rest of the network and so on. But CNNs are designed in a different way. So when you're dealing with CNNs, you can give it grids. And we're 6 weeks away from that. Got it? So initially, all of our images will spaghettify. And they'll go in like that. Okay? So this assumption that I'm doing here, this one, is assuming every image is being spaghettified. Right? So, right? Okay, so I get an image, which by the way can have 2 objects apparently, unless we space them out really well and we take a picture only when, there's quite a bit different ways of doing it, but I'm going with this right now. So we say this image is 224 by 224. I'm going to spaghettify it. Therefore, I'm going to have a vector that is 50,000, has 50,176 features. So that's really F2 all the way to that number. We say that is R5176. That's the dimensionality of it. Okay? It's big, but a GPU can handle this, probably. It's big, yeah. So what's a sample then? We need to give it a formal definition. So what's a sample? Each image that we've spaghettified. Therefore, every row in X is a sample, correct? So we'll say S1, S2, all the way to what? How many samples will you have? 255 samples. So 255 is the dimension of the features, right? But I'm asking how many samples, like how many going in this direction? So why 70,000? It's a big number. Well, you have to provide a little bit more justification than that. But I don't think you're wrong because it seems reasonable. You're in, you have to think of the environment that you're in. You're in a factory, right? So it's not like electronic stuff, like pictures from my iPhone. You can get millions of those, right? This is a little bit more limited because it's a picture of a physical thing. Do you guys see that? The production of these widgets. So imagine it's a factory that you have to like start quantifying. Okay, it runs for 8 hours in a day, this conveyor belt. And how many of these things go by? Do you see that? And how often is it a sampling, or do you take a picture of every single one? Do you see that? So you have to quantify that a little bit more. And then how long do you collect this data for? Let's say you collect it for, let's say it runs for 8 hours. And every hour, how many of these might go by? Maybe 10 an hour. Yeah, 10 an hour, let's say, to keep it simple, right? So 10, these are complex widgets, yeah. So so you get 10 an hour. So then it's 80, right? A day. And then you collect this for 10 days. So 800. Do you see how you arrive at that's really what matters, right? Is that you can say, well, actually, I can't have 70,000 in that. But if you were thinking, no, I want a minute, that might be 7,000. Do you see why that's important? Because collecting data can be very expensive. This is expensive, right? A little bit expensive, I should say, because it's physical things. So which value do you think is more accurate? 70,000 still, or 800? What would you go with? Obviously, we have to define what this widget is. Maybe it's something that a machine melts and then extrudes. I don't know, something like that. So just give me a number. 9,000, sure. 9,000. It seemed, not as much, but also 800 seemed kind of low. Good. All right, so this is 9,000. This is important also because, okay, that means you have 9,000 samples. If you only had 3, that's really bad, right? So you want to have deep learning algorithms require a lot of data to learn. They're not like a little kid, trips on this wire 2-3 times, that's enough to understand. The analogy here is deep learning would need to trip on this like 100,000 times before it starts to learn not to trip on. So it takes a little bit longer because of how it, in a plain vanilla neural network. Does that make sense? All right, so I've defined this. Now, X is defined, right? We know it's the pixel values from 0 to 255, 9,000 samples. Features is 50,000, which is really large. I would not build a neural network like that. For images, if you will learn later that when we use the grid with a CNN, it's actually smaller dimensionality, but that's, so it runs faster actually, which is counterintuitive, but it's better. It's just better algorithm. All right, so now we need to define Y, right? That's still undefined. So what is this value here? Good. So it's the same value, 9,000 exactly. Why? Because this is, a supervised learning problem. So for every sample, we need to have some kind of a correlation, right? A label. So yes, exactly. This one is 9,000. Very good. And then here, this value we still need to define as well. So this is 50,000. This represents, by the way, the thing we're predicting. So the classes. What were the classes? Do you remember? Good and bad, right? So this one has a crack, a defective piece, and this one. So maybe actually +1 because it's good, -1 because it's broken. So it's a 2-class problem, right? For a 2-class problem, we really just need 1 column, right? So then it's gonna look like this, probably. -1, 1, 1, 1, -1. Do you see that? And this value is, do you guys understand? So if you think like this, when you're analyzing any machine learning problem, you're already getting into what's my architecture, what's my code look like, what is X and Y and all of that. And you're just putting everything in the correct format. All right, so we can probably do another one, right? So we can try another one. So let's see. We'll need to go back to the word descriptions. I need to share that. All right, so these look.
Okay.
Yeah, go ahead.
Just no front phone. The X dimension. What's the difference?
The X matrix and the X dimension.
In your, just in your question.
I think I was just saying, what is the dimension of X?
Okay. You just-
The same thing, yeah. So what is X? And then give me the dimensions for it. Yeah,
Sorry.
it's the same. No, it's the same. But it's important because that tells you number of samples, number of features, that tells you the architecture, tells you it's a classification problem, all those things. All right, so we have detect debris in outer space. That's probably like a camera also, so it would be a similar type of a thing. I think I'll do a network security one. Let's do like an intrusion detection systems one. So I think I have that. Oh, sorry, I meant to go. I have that in the other set of problems. All right, so let's look at these because here I have more problems. I don't have it. I think maybe that's the exam question. Okay. All right, but let's do that one, right? So let's do an intrusion detection system one. So I'll just like elaborate. So, we all know about cybersecurity, of course. So this is a cybersecurity problem, right? So cybersecurity, and in particular, it's an intrusion detection system. So you've been hired by Cisco or something, and you're in the machine learning department at Cisco, and they're developing this new machine learning based appliance for intrusion detection of network attacks and things like that. So how do we approach it? We can take the pretty much the same idea. What is X? What is Y? Right? And that can start to motivate everything else that we're gonna do. Now, this intrusion detection system needs to also detect denial of service attacks. So denial of service attacks are the kind of attack where you have a server and it's being flooded with network requests. So everything in the network works through something called a packet, right? So maybe you guys have heard of that. So you have, between two computers, the electric wire, and you're sending zeros and ones, but in little packets, right? In specific format. So what's going to happen in a denial of service attack is it's going to be thousands, millions of packets hitting that server, trying to overwhelm it. So they bring it down so that people can't get their services. Okay? So we've defined that. So let's say there's some kind of a network cable, in the company, it's two areas, A and B for some reason. And then here we have our computer, our IDS. Okay? And its goal is just to detect, nothing else. So it's an intrusion detection system. So now, okay, you're going to build a machine learning algorithm, some neural network possibly, but before we get to that, we want to define X and Y, right? So how do we do it? We need to start answering the questions. So samples, what are the features? What are the dimensions of X and Y, etc. So how do you do it? Yeah, please. Data and time as features? Okay. So we have features. So you're like engineering every feature here. So Data in the packet?
Yeah, like, yeah, how many packets from a certain amount of time?
Mm.
Thousand packets of data, million packets of data.
Okay. Okay. I like this one. So think about what you're saying, right? So number of packets per time. So, okay. So what's the sample? That's the key thing. Answer that. You're not wrong. I'm not saying you're wrong,
Yeah, no,
but define the packet. What's the packet in this? Oh, sorry. What's the sample in this context? What's the sample? Because we need the rows, right? We need to know what the rows are going to be. And we know that the rows are samples. You know, M or N, is it N to M? So the first question here then that I ask you, because I like your idea, but what is the sample here? That's what he said. So that's your definition of it then. Not the normal traffic per se. That's actually getting more into the classification problem, the labeling of packets collected. Okay. All right. So you're all right. So let's go with that. So, and then what I would say is, okay, the simplest thing that I can think of is that every sample is a packet. So one packet. I'm not even looking at time. I just grab a packet and I'm gonna have some label associated with it, like attack, not attack. Do you see that? That's the simplest. But you're saying you don't want that. You're saying actually, I need some kind of a window of time. So just to keep it simple, every minute, right? So you collect data and then you save it, and then the next minute collect data and you save it. All right, great. So we need to write that in some way, but essentially the sensor needs to do that, right? It's code. At minute 1, it starts recording. At minute 2, saves that and starts recording again, saves that, and it's like these little buckets where you're throwing things, right? So actually, let's do that. So it's like a bucket, 1 minute, and what are we throwing in here? Hmm? Packets. Okay, so it's not just one packet, but it's how many packets went in there, right? In a minute. Okay, there's a problem there that we need to address, not that it's wrong. So we have another minute when there wasn't an attack. So here we received maybe 100 packets or 1,000 packets. In this one, we only got 3 packets. How do you compare one to the other? Do you see what I'm saying? So visually, imagine it. You have here one packet, they're TCP packets, for instance. You have another exact packet, dot, dot, dot. Whereas here you have one packet. This one is obviously bigger than this one. How do you deal with that data? Do you see what I'm saying? It's not wrong, but it's so what would you suggest? Because they need to be similar, right? The features here need to be the same for these and for these. Hmm? We do a small picture. Oh, in the last example, like compress it into a small picture. Okay, I see. I think I know where you're going with that. Okay, yes. How about we just calculate statistics of the packets? Do you see what I'm saying? So instead of keeping all the information of the packets, let's just calculate statistics, like a distribution of these packets. That way, that's going to be the same. So for instance, mean and standard deviation. So let's say I have 2 packets here, right? And then here I have like 5 packets. So this would be way more data than this. That presents a problem. But I just take the mean and the standard deviation. And then I take the mean and the standard deviation. Do you see that? So now I just have one mean for one mean for the other. I can compare them. So those could be F1 and F2. Does that make sense? So this way, it allows me to do your idea of collecting the number of packets per time, but I also address the fact that this could be 1,000 packets and this could be just 3. Way more data here. So they need to be somehow comparable, right? Because we're saying F1 needs to be something, a feature of this sample. Do you guys see what I'm saying? Any questions? So, but that's not all we do. So you might not like this idea because you're like, but I'm losing information. Well, you're a feature engineer. Engineer more features. You see that? So, okay, F1 and F2 were the mean and standard deviation of the 5 packets for that sample. This is sample 1. And then this is sample 2, another time window with just 2 packets with a mean and a standard deviation, F1 and F2. But now you can also have one feature, F3, which is like the grade feature. What does it do? It counts the number of packets that came in that period of time. So F3 for this one is 5 or 1,000. For this one is 2 or whatever it is. Do you see what I'm saying? So you do these statistics, summary statistics of the time period. Yeah.
Okay.
The mean is, like if I have 2 values, 2 ages, 32 and 35, 30 and 35, that comes out to like 33. That's the mean. Oh, okay. Well, then that's a good question. So now you have to think of the structure of the packet. So we have to first make an assumption. What type of a packet? Is it an ICMP packet, a TCP packet? If it's an ICMP packet for whatever reason, it's going to have headers, Ethernet, the IP header, and I think there's a content and things like that. So now you select each one of these headers has like 20 variables. So for instance, one variable might be like number of bytes sent, number of bytes, number of bytes sent. Another one could be the protocol, right? So protocol 6, I think. This is a bad example, but could be the port number, port 80, port 22. So they all have, one thing they have, this is a good question. One thing they have is they all have a port number. They all have, what did I say? Bytes sent. They all have it. So now you just touched on something. Instead of just F1 and F2, we need a feature for every of these. We take the mean of the number of source ports and the mean of the number of bytes sent and the mean of the standard deviation of, so that's how you start to build the feature. So assuming we have, let's say for the sake of argument, every packet has 40 variables and all of those are relevant, then you would end up with 40 means and 40 standard deviations. Because you're a feature engineer, you can do that. That's actually your job there, is to do collect the data raw and then write that code, that data wrangling that I was talking about, to create this vector space. Do you guys get it? Will it work? I don't know. You have to try it, but this is how you would start to approach it. You see that? So I like your example because, to me, if I was just going to lecture this, I'm going to go the easy route, right? I'm going to do one packet and that's a sample. But if a more accurate one might be number of packets collected per 1 minute. But then probably statistics. If I'm lazy, I'm just going to average them all and that's it. Because they're all the same packet, 40 variables. So I'm just going to create one packet that is the average of all of them. And when I write my pipeline from beginning to end, I'm going to test it. Once I know it doesn't work, then I start doing the other things. Any questions on this one? All right, so what have we done? So let's say we've defined what a sample is very well. How many features? So now we have an idea of how we would approach the features. So how many features do you think we end up with here? Why 81? Yeah, that's pretty precise, right? Yeah, all right, 81. Yeah, exactly. We had 40 variables in the packet. So 40 for the means, 40 for the standard deviation, and then one feature because we count how many came in that time period, which might be, by the way, the most important feature when you're detecting denial of service attacks. Mm-hmm.
Was that thought?
Mhm.
What?
Yeah, no,
It's just counting.
yeah.
Come through.
So you can keep track of, if you have a timestamp, you can keep track of when it happened, and that's another feature. So we have 82 features. Yep, exactly. I mean, there's no right or wrong answer, is what I was trying to tell you. How will you know? Think of it like you're a consultant, right? And you get hired by some company to do this. I mean, it either works or it doesn't, and then they're gonna pay you or not. It's essentially how it works. So that's the idea. You want to make it work, and you build a simple pipeline, the simplest you can, just to have something, and because that also helps you to start thinking through the problem. Sometimes you have an assumption of what you're gonna do, and when you actually do it, it's like totally wrong. So this helps you out. All right, so 81, 82 features, that's great. We've defined that. What is N? This gets at another big part of this. So imagine the university. There's a lot of packets, right? There's a lot of network traffic. But how often is this network being attacked? Really? Compared to how much good traffic. You guys are experts in this, right? What do you think? Like 1% or 50%? 1% probably. Yeah, closer to 1%. That's what I would say, right? Otherwise, we'd have a problem, I would think. They probably hire a new security team, right? So I would say it's probably a small percentage. So this is another problem in machine learning. Machine learning likes balanced data sets. And what that means is it likes an equal number of classes on one side and the other side. So it would want to have, if there's 50,000 collection samples for good traffic, it would want to have 50,000 for bad traffic. Do you see that? That's like a key thing in machine learning. Once you start to deviate from that and your data set becomes imbalanced, you have a problem. And then you have to then think about the algorithm, like an anomaly detection system or something else other than a classifier, like this type of plain vanilla classifier. So we need to quantify this, right? So first of all, how are you even going to get the attacks? That, maybe they have very few attacks that have actually happened. So maybe you have to simulate attacks. So you have to create like a controlled environment. And even then, you have an imbalanced data set. So what do you guys think? You have to tell me a number. How many? It's network, so it's all electronic, so definitely you can generate a lot. And if you create your own kind of fake or honeypot environment or something like that, you can run a lot there still. But for the sake of argument, I think there's a famous IDS called KDD. I think it had like 100,000. So for the sake of argument, let's say there's 110,000, because it's not even packets. This is actually time windows, right? And so that's also another thing. And we're going to be realistic, and I'm going to say this is highly imbalanced. So 95% of these are good traffic, 5% are attacks, so bad traffic. You see that? So that's important. So how do you collect this data? Well, if it's a simulated environment, let's say this is the simulated environment, you grab your laptop, and you just go to Google, go to email, Facebook, whatever, right? That's good traffic. You're not attacking anything. Do that one day. And as you're doing that, you're collecting all that data with Wireshark or something, saving it in a file. Do you guys get that? Tomorrow, you designate the attack day. This is just a simplification. So then I, again, put my laptop in the network, take out like NetWalks or Kali Linux or something, and just start attacking the network, collect all that traffic with the label attack traffic. Do you guys see that? Same approach, but now you will have your labels. Yes, please. If I still think, well, in a real network, you always kind of want to be like what would be in the real network. And in the real network, it's not going to be balanced, right? Like it's a better example, fraud in a bank. If you have so much fraud in a bank that it's 50% of good transactions, that's like the FBI is going to show up there, right? It's a seriously badly managed situation. So you could, another approach could be you just do bad, right? However long this takes, and then just collect the same amount of samples for good. So it's balanced, but how realistic is it? I don't know. And it's the kind of thing that you have to do some research and figure it out. You have to test your model, because that's another thing. If you make this 5%, and instead of collecting all those samples, you also just have that similar 5%, the model is balanced towards detecting attacks. Do you see that? And that doesn't happen as often. So what you end up with in this situation possibly is a lot of what are called false positives. So it's going to flag a lot of things as attacks that are not. Do you see what I'm saying? Because you're overemphasizing that in a real environment, there would be these many attacks. So I almost have to like figure out how to label everything an attack. So this is a complicated problem. You have to really work it through like the people there and try several things and then arrive at something that you think is useful. Okay? Any questions on this one? All right, so what have we defined? We know 110,000. We knew the labels. That's pretty easy, right? Attack, not attack. So then we said this is 100,000 here, N. So obviously this one is also 110,000 because we have to have a label for each one of these buckets. And then this value is just 1, right? Because it's going to be attack, not attack, or the opposite. Just like that. Yeah, go ahead, please. How do you mean? Not which kind, just if it's an attack or not an attack. So remember the way that I collected the data, it's a kind of like the easiest way that I can think of, which is like this. Monday, I'm gonna collect the data, right? In the same approach, buckets, all the packets. But on Monday, I just go to Google, I just do email, I just search the web. Whatever I'm doing, remember, it's all going through the network as packets. So that data that gets collected gets labeled as good. But I'm not keeping track of whether it's going to Google or going to, just it's what happened when I was just doing normal traffic. But the next day, I come to the network, I plug in my computer again, but this time I bring up like an attack tool because I'm going to simulate attacks like denial of service attack or something. And then on that day, I do the attacks and I'm collecting the data and I just remember to label that as attacks. And then I let the machine learning algorithm learn what an attack looks like.
So my question is
Yeah.
that
Not necessarily, actually, because an idea is just an intrusion detection system. It provides like a list of it found an attack, and it might give it like a rating, and then a human can inspect it after the fact. But it doesn't have to. Are you saying that I should also like prevent it or something like that? Oh, yeah. Okay. So if that's your concern, well, two things. First of all, we're just kind of, no, I get you. Right. So yeah, I see your point. So first of all, we were just looking on how to create X and Y from a problem, first of all. But actually, intrusion detection systems, you guys are experts in this. So most of the time, they just like collect the data. I think it's called an intrusion prevention system, the IPS, which is the one that might stop the firewall, for instance, like might put a rule in the firewall to prevent that IP from coming back that was flagged or something like that. But we're not concerned with, for our example, in preventing it, just detection. Remember, it's a classifier. So if I have a cat and a picture of a cat or a dog, all I say is cat or dog. That's it. Okay.
What's the solution if we want to take which kind of attack you are facing?
Or prevented. Because that's this was one problem. You just gave me two more that I would have to think about. Do you see what I'm saying? So if you want finer grain detection, then I would need to, when I collect the data and I put for the simulation, I'm going to say, right now I'm doing denial of service attacks. So now it's got another label. It's not just a two label problem, but it's potentially a 10 label problem. Yeah. Or I get your point. I would argue I would do it differently. I would have two models. One model that says good or bad, and if it's bad, it gets sent to the second model. And the second model now says which of the attacks it is. Do you see what I would do it that way? Because if I give it 1,000 labels, it's not going to do very well. So two labels is like how I would want to do it, and then okay, move it to the second model and have that second model figure out if it's like one of three types of attacks, and then I send it to a third model which can give me more information, but that's still just detection. Because prevention in networks is just like putting rules in the firewall or something like that. So that's, I think, a different problem. Anything else? Make sense? All right, perfect, perfect. All right, so I think we arrived at this one, right? The X is 110,000 by 81, and this is 110,000 by 1. And we explored a really nice scenario where the packet is not the sample, but actually a time window where we collect things. Got it? All right, so I think we have time for one more, right? Because we have 16 minutes left. All right, so let's take a look at one more. So let me stop. Oops. Let's go back to let's do number 5. What do you guys think? That's like a fun one. A classification model for movie recommendation, e.g. Netflix, right? So a recommender system. We deal with this every day, right? If you go to Amazon, when you turn on your TV with Alexa or something, recommender system's going on. So let's do that one and we'll wrap up with that. We'll use whiteboard. So just to give you this like note about recommender systems, there's actually a whole field of machine learning for recommender systems. It's called collaborative filtering, first of all, right? So it's a whole its own area. It uses techniques like something called singular value decomposition. So there's actually specific techniques and algorithms to deal with that problem effectively. Netflix used to do the Netflix price, which is like a competition where people would try to build a better recommender system, and whoever won would get like $1 million or something. This happened like 10 years ago. If you remember Netflix, when it started, you actually had to say which movies you liked and before you got started with it. So this is a real thing. So anyway, my approach here is just to follow this same template, right? So we're going to follow the template, build something, but it's not collaborative filtering. It's not, that specific set of techniques for recommender systems. So again, a recommender system, start again with the same process. What is X and what is Y? And in particular, we want to have those dimensions. We need to define what we're trying to do. What's our goal with this recommender system? What's a sample? So what do you guys think? And what are the features, of course? So it's movies, but a movie is, a video, but we're not going to do like image-based things. Instead, we're going to think of each movie as more like the metadata of it, right? The metadata of that movie. Genre, everybody says genre. So what is genre then? What's a category? I don't know what that is. We have to use the right words, right terms, right? So we got features, classes, feature. Okay, genre is one feature. Okay. So I'm going to start over here, F1, genre. Okay, so that's like action, comedy, something like that, right? Okay. What else? Length of the movie? Okay, how long it is, right? Yeah. Okay, so 80s movies, I think were like an hour and a half. Today, movies are like 3 hours or something, right? So length. True. Okay, so length of movie. All right, so you guys are doing feature engineering. You've decided, you know what? I'm just going to think of every possible feature. That's called feature engineering. So how many of these features do you think you'll end up having? 200? All right, 200. Or 1,000 or 2,000. What's more likely, 200 or 200? Okay, 200. So this gives us an idea that seems to be enough. All right. And then what do we do? What's the model do? We give it these features that represent the movie, and then what? Correlate, sure, but what does the model actually do? Like it's a classifier. What does it predict? If you will like it or not. Okay, I like that. So that's a classification problem, and it's saying you'll like it or not. Like, not like. So that's classes. Like. Sure, you can have more. So how many? You tell me. 4. Okay, so 4 classes. What are they? Like, not like? What else? Okay, all right. So like, yeah. Okay, yeah. So 4. That's fine. 4 classes. Let's call it, just to simplify, I'm going to call them C1, C2, C3, C4. All right, great. What else? What is a sample? You see how it always kind of comes down to what is a sample, right? So what is a sample? Maybe it's easy. What's a sample? One movie. Okay, very good. So I have a movie. Can I use M here? Movie 1, movie 2. How many movies then? Just 100 movies? There's more than 100 movies.
10,000.
It's Netflix, 10,000. Okay. So the number of samples is 10,000. And you can think of it this way, right? So you're training this now, and you're going to be using it in the future. So new movies that come in will have these features, and the model will predict if you're going to like it or not like it. Do you guys agree? All right. So I have did we say 10,000 or, oh yeah, 10,000. So 10,000, a sample is a movie, and then we have F200. So we have the 10,000 by 200. This is 10,000 by still one, whether you have two classes or four classes. Later on, we're going to learn that we can one-hot encode these things. So what that means is that we would have, instead of one column, because there's four classes, we would have four columns. And if it's this movie, then this is a one and these are zeros. And if it's this movie, then these are 0, 0, 1, 0. That's called one-hot encoding. Machine learning models sometimes learn better this way. But that's something we can look at a little bit later. Especially when you like start to have a lot of classes. Yeah, go ahead, please. Yeah. Yeah, it's the row. So one simple way of looking at it is a sample is usually the row that's correlated to a label. So in this case, it's a movie because a movie comes in and it goes into the model and the model should say this person will like it or not like it. Do you see it? Do you see that? Yeah. Definition of sample is the thing that goes into the model, right? So that's usually the sample because what goes into, you have a neural network, right? Like that. What goes in is the features, all the features, right? So that's going to be all of these features in one row. And what comes out is the predicted class, like, not like. So a sample essentially is whatever this vector is. So in this case, it's a movie. Sometimes if it's a cat and a dog, what is the sample? The image that goes in of the cat, and then it says cat. In the network intrusion thing, what was it? It was that bucket, right? Of the packets that we would calculate the statistics for. And not in that problem, right? So that was the whole point of that problem is that I said a sample could be a packet, but you guys, some of you wanted a time window and collect all the packets. So that was defined as the sample. And that's why we had to do the whole statistics and all that. Do you see that? So yeah, understanding that concept is pretty important. But in this scenario, what goes in here is a movie. And we don't even look at the video or audio of the movie, just metadata of it, which you guys have decided it's about 200 metadata features like genre, length, Tom Cruise, present, not present. What else? Rating, right? All those kinds of things. So that's a very feature engineering heavy, machine learning problem. So now, the labels are going to be, so for instance, now we have to think of the labeling scheme here. So there's all these movies. We already established they have a genre, a length, so that across all of them, that's consistent, right? So then a person comes in and they look at the Matrix and they say, I like that. And they look at Star Wars and they like it. And they look at Star Trek and they like it. But then they look at You've Got Mail, they don't like it. And they look at Casablanca and they don't like it. So you see, I'm going with a theme here, right? So the ones that you like were like science fiction, and the ones that you didn't like were like romance kinds of movies. Do you see that? So that annotation happens. What the model will learn there is to correlate, okay, genre, sci-fi versus romance should correlate. So if you look, these science ones, genre, let's imagine genres here. So sci-fi, 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 romance, romance. There's almost like a perfect correlation between romance and not like, and sci-fi and like. That's what machine learning learns, these things. If the length of all of these is, let's say, 100, which whatever that is, all of these are 100. That's a useless feature for machine learning because it's not able to differentiate anything. It's 100 for all of them. So what helps it to differentiate here, and that correlates. Got it, guys? So then we're going to train this model, right? And this model learned that, sci-fi is preferred. So then now when you use it, you get a movie like Spaceballs. I don't know if you guys have seen that. It's an old 80s movie. And so that movie, what is that movie? It's sci-fi, but a little bit comedy. There's some romance. So what is it, right? So that's maybe a difficult thing for the model because there may be other variables involved. So it may get it right sometimes, sometimes not. But then it gets, what's another, the Matrix, did I say that one? So the Matrix is another sci-fi. Maybe that one aligns more with these, so it would be predicted as like. Got it? So that's a very crude recommender system, not based really on how they work, on Amazon, on Netflix today, but definitely we're able to define. So this is also 10,000, right? And this is still one because it doesn't need to be one hot encoded. And this was 200. And by the way, we don't have to define all 200. You get the idea of how it would work. Any questions? All right, so it's 917, or 918. So it goes from 6:30 to 7:30 to 7:50, and then from 8 to 9:20, right? So we end at 9:20. So we can stop here for today. So I'll end this.